Hey folks, this is week 11 preview video. You're going to do some more work with logarithms. And early in the week, the first section, you're going to see some of the laws of logarithms, or the book may call them properties of logarithms. And I've summarized them here. The first one, it says when you have log base b of x times y, you can rewrite that as log base b of x plus log base b of y. So the log of a product can be rewritten as a sum. Number 2, log base b of x divided by y. Well, that can be rewritten as log base b of x minus log base b of y. In other words, when you have the log of a quotient, you can rewrite it as a subtraction statement. And then the third one is when you have log base b of x raised to the r power, well, you can rewrite that as r times log base b of x. Let's do an example of using these laws or these properties of logarithms. So the first one I have here is you have the natural log of a squared b cubed over c to the fourth. And our goal is to just rewrite it as, or to expand it out as far as we can using these properties of logarithms. Well, the first thing I notice is I have the log, it's a natural log, of a quotient. So I can use logarithm law number 2 to rewrite this as the natural log of a squared b cubed minus the natural log of c to the fourth. So that's using number 2. Now notice here I have the natural log of a product. This is a squared times b cubed. So I can use property number 1 to rewrite this first term here as a sum. So that would give me the natural log of a squared plus the natural log of b cubed minus the natural log of c to the fourth. And finally, if I use number 3 here, I can take all of these exponents and move them out in front as like a little constant multiplier. So I can finally move this 2 out front to get 2 times the natural log of a. I can move the 3 out front to get 3 times the natural log of b. I can move the 4 out front to get minus 4 times the natural log of c. And I can't go any further. I've expanded it out as, well, as far as possible. Let's do another one. So part B, let's look at the log of square root x times y cubed. So hey, a quick review from last week. Remember when you see natural log, remember that has a base of e. When you just see log, this is a common log, it has a base of 10. Okay, with that review underway, I have a product here. So thanks to property number 1, log of a product can be rewritten as a sum. I can rewrite this as log square root x plus log y cubed. Now folks, remember square root x can be rewritten as x to the 1/2 power. So let me go ahead and rewrite square root x as x to the 1/2 power. And now I can use property number 3. I can move the 1/2 out front. I can move this 3 here in front to get 1/2 log x plus 3 log y. And that's as far as I can go on that one. So those are the 3 laws of logarithms. Here's 2 very quick examples on how to use those laws of logarithms to expand out as far as possible a condensed logarithmic expression. All right, hey, last week you saw preservation of equality, or your book called it the method of relating bases for exponentials. There's a similar thing when it comes to logarithms, and that should make sense because remember, logarithms and exponentials are basically, they're inverses of each other. They're related that way. So here's my preservation of equality for logarithms. Log base b of x equals log base b of y if and only if the x is equal to y. So let's do a couple of quick examples on how we could use this preservation of equality to solve some equations. So, quick example. Let's say we're asked to solve log base 11 square root x equals log base 11 of 6. According to the preservation of equality, since we have the same base, log base 11 and here's log base 11, the only way this equation can be equal, the only way it can be true, is if square root of x is equal to 6. Like if I just square both sides of this equation, I get the solution of x equals 36. Let's do another one. That one was pretty friendly. So here's a second one. Say we're asked to solve the natural log of 5 plus the natural log of x equals the natural log of 7 plus the natural log of 3x minus 2. Okay, now this one's going to take a little bit more work. We're going to have to use some of those laws of logarithms to kind of help us get to a point where we can use our preservation of equality. For example, the left side of the equation is the natural log of 5 plus the natural log of x. Look back at law of logarithm number 1. This is an addition, so I can condense this down to the natural log of 5 times x. Likewise, on the right side, I have an addition, so I could condense it down to a single logarithm, and it would be the natural log of 7 times 3x minus 2. Now I have it at a point where I can use our preservation of equality. The only way this equation can be equal, because both, remember, natural log has a base of e, the only way this equation can be equal is if 5x is equal to 7 times 3x minus 2. Well, that's a pretty friendly little linear equation to solve. I mean, heck, you just distribute the 7, subtract 21x from both sides, and 5x minus 21x is a negative 16x. Divide both sides by negative 16, and negative divided by a negative would be positive, so that gives us 14 over 16, which reduces down to 7/8. So as you can see, first one that I did was pretty straightforward, just using our preservation of equality, whereas the second one required us to use some of our laws of logarithms to help us in order to solve the equation, in order to then use the preservation of equality. In any event, there's two quick examples of solving some logarithmic equations. Hey, you're going to learn about this thing called the change of base formula. It's a handy-dandy little formula that allows us to evaluate the logarithm of any base. Keep in mind on your calculator, when you look on your calculator, you actually see a log button and a natural log button. You don't see a log base 7 button or a log base 13 button. And this formula came about as if you wanted to evaluate the logarithm of any base. And what the change of base formula says is if you have log base b of x, you can rewrite that as log of a over x divided log of a of x divided by log base b, log base a of b. So again, log base b of x equals log base a of x divided by log base a of b. It can be any base, folks. So for example, this is a very quick for example. Let's say you wanted to determine log base 4 of 10. So like log base 4 of 10. Your change of base formula, it says you can rewrite it using any base as long as you keep the bases here the same. So that means you could, to determine log base 4 of 10, or the log of 10 base 4, in order to do that, you could rewrite it as log of 10 over the log of 4. Here I'm picking the base to be 10. I would pick the base to be 10 because I see that's one of my buttons on the calculator. Or I could have rewritten this as the natural log of 10 divided by the natural log of 4. Again, I picked natural log because I see that it's a button on my calculator. And so what I'll ask you to do is, if you use your calculator and you do log 10 divided by log 4, you're going to get a decimal. If you do natural log 10 divided by natural log 4, you're going to get the exact same decimal as you do here. You have to get the same thing. That's what the change of base formula says. And that's pretty much it for the change of base formula. Okay, next up you're going to see a section that's just a whole bunch of exponential and logarithmic equations to solve. When you're in this section solving, anything is fair game. You might have to use some laws of logarithms. You may have an opportunity to use the preservation of equality for exponential functions that I talked about and you learned last week. The preservation of equality of logarithmic functions, that too could be used. So it's kind of like right now, anything is fair game. And I thought we'd look at a few examples to kind of get started, help you get started in this section. So the first one is solving 4 to the x equals 11. Okay, if I could rewrite 11 as 4 to some power, I would do it and quickly use my preservation of equality of exponential functions. But I do not know 4 to what power. I don't know what that exponent is that would kick out a result of 11. I don't have that much free time on my hands. I just don't know that. So here's how I solve an equation like this. You know, I'm trying to solve for x, and that's in an exponent position. So I'm immediately thinking logarithm is my friend. And then I have to make a choice. Do I want to use log, the common log, or do I want to use natural log? It doesn't matter which. So I'm going to use natural log. Now watch, I'm using the preservation of equality for logarithms. The preservation of equality says this equation is true if and only if the natural log of 4 to the x is equal to the natural log of 11. That is the preservation of equality of logarithms. Now why would I want to take the natural log of both sides of this equation? Well, we have a property, a law of logarithms. I think it's law of logarithms number 3. I can take this variable that's in the exponent position, I can use a law of logarithms, and I can move it out front to get x times the natural log of 4 equals the natural log of 11. Now algebraically, there's just one more step in solving this equation. Divide both sides by natural log 4. And I get x equals the natural log of 11 divided by the natural log of 4. That is the exact solution to the equation. So let me make a note here. This is the exact solution. If I fire up my calculator and I do natural log 11 divided by natural log of 4, I will get a decimal approximation. So natural log 11 divided by natural log 4, when I fired it up, my calculator, and did it, I got a 1.7297. And that is a good decimal approximation. Let's try another one. So let's say we wanted to solve a 150e to the x minus 4 power equals 5. Okay, that looks a little more involved than this equation we solved, but it's only a little bit more involved by one more step. Your first step here should be to divide both sides of the equation by 150. You divide both sides by 150, you get e to the x minus 4 equals 5 over 150, or e to the x minus 4 equals 1/30. Okay, now some would say, oh hey, let's take the natural log of each side of the equation, which is fine, you could do that, But do you remember back in last week's video and the homework you did last week? I made a big deal about being able to write an exponential equation in logarithmic form and a logarithmic equation back into its corresponding exponential form. That's what I'm seeing here. The base of this exponential equation is e. So I should be able to immediately rewrite this into logarithmic form. I should be able to rewrite this as x minus 4 equals the natural log of 1/30. That's just going from exponential form to logarithmic form, a skill that we practiced last week. So now how do I solve for x? Well, quite simply, just add 4 to both sides. And I get x equals, I add 4 to both sides, 4 plus the natural log of 1/30. Which again, this is the exact solution. If I fire up my calculator and I do 4 plus the natural log of 1/30, I get a decimal approximation of 0.5988. So that's the exact solution, that's the approximation. So there's a couple of examples of how to solve some of these equations. I have a few more to do, but the first thing I have to do is erase the board. So give me a minute while I erase the board. All right, hey, I thought the next equation we'd take a look at solving was this beastie. 2 times log base 5 of the quantity 3 minus x minus log base 5 of 2 equals log base 5 of 18. So this looks a little bit more involved than B, and well, let's check it out. What all do we have happening here? Looks like we're going to have to use some of those laws of logarithms. First law of logarithm I would use over here on the left side is this 2 that's here. I can put that 2 back up here in an exponent position using property 3 or law 3 of logarithms. So that's what I'll do first. Rewrite this as log base 5 of 3 minus x squared minus log base 5 of 2 equals log base 5 of 18. Now here we have subtraction. So property 2 of logarithms, or law of logarithms number 2. We can take a subtraction and rewrite it so it's the logarithm of a quotient. So that's what I'll do next. This is log base 5 of 3 minus x squared over 2 equals log base 5 of 18. Okay, I finally have the equation at a point where I can use the preservation of equality of logarithms. I have log base 5 of this mess equals log base 5 of 18. This equation is true if and only if the 3 minus x quantity squared over 2 is equal to the 18. Wow, well now let's look at solving this equation. Got a little bit more algebra to do, folks. You multiply both sides of the equation by 2. And that gives me that. 3 minus x quantity squared equals 36. If I FOIL this out, see I get a 9 minus a 6x plus an x squared equals 36. And I'm running out of room, so let me kind of pull it up here. And as I pull it up here, I'm going to bring the 36 on over to the left side. So I'm going to subtract 36 from both sides and rewrite it. So I have an x squared minus 6x. See, 9 minus 36 gives me a minus 27 is equal to 0. I just rewrote it in a descending order form. But I hope that factors. Because if it doesn't factor, I have to use the quadratic formula. So let's keep our fingers crossed that this beastie factors. So I have an x here and x here. Thinking of factors of 27, the ones that jump out at me are 3 and 9. 3 and 9, so let's see if I can get the correct signs in there. I think it's plus, minus. And that's the correct factorization. Set each factor equal to 0, and you get x is -3 or x is 9. And right now, if you're thinking, all right, sweet, we've solved this equation, no, we're not done. You have to check the solutions. We haven't had this issue yet, but we do on this one. We have to check our solutions. We don't want to count a solution that is said to be an extraneous solution. Extraneous is a fancy word that means bogus. It doesn't really work. Look at x equals 9. Toss that value of x. Let's put it back into the original equation. Put it in for x. Put it in for x. 3 minus 9 is -6. Can you do the logarithm of a negative number? No, you can't. We talked about this last week when we talked about domain of logarithms. You can't take the log of a negative number. So this solution does not work. It is, books call them extraneous. Fancy word that means bogus. We should probably check the -3. If I put -3 in for x, well, 3 minus a -3 is a +6, so I feel pretty good about that. I can do the logarithm of a positive number. And in fact, that if you actually finish off the check, you'll see that that does check. It really is a solution. So here's how you would solve an equation like this. We had to use a couple of laws of logarithms, preservation of equality, and then a little bit more algebra, and at the very end we had to check our answers. We can't have bogus answers. And, oh, you know, I have another example to look at, but first, yeah, I'm going to have to erase the board, so give me a minute to erase the board. We'll be back to look at another example. Ah, here we are back, part D. We're going to solve this equation. This one looks pretty friendly, actually. We have log base 3 of 2x minus 5 equals -2. That is a single logarithmic equation. We should be able to immediately rewrite that as an exponential equation. Stuff we did last week. So I can immediately rewrite this in exponential form. 3 to the -2 equals 2x minus 5. And now it's just a matter of, it's a Nike problem. We just do it. 3 to the -2, well, that's 1/9 is equal to 2x minus 5. And if we add 5 to both sides, well, I need a common denominator. 1/9 plus 5. Let's see, 5 is 45/9, so 1/9 plus 45/9 is a 46/9 is equal to 2x. And then if we divide both sides by 2, we get 46/18 equals x. And then 46/18, that reduces down to 23/9 is equal to x. So that equation wasn't too bad. It was actually kind of friendly. And I think I have enough room to put part E over here. I have one more equation to solve, so I might as well get it up here now. Let's solve log base 7 of x plus 9 plus log base 7 of x plus 15 equals 1. Okay, so for this one, we have to start off using law of logarithms. In fact, law of logarithm number 1, we have an addition over here, so we can rewrite that as a single logarithm, but as a product. So I can rewrite this as log base 7 of x plus 9 times x plus 15 equals 1. And now just like here, you know, our first step here was to rewrite this logarithm into exponential form. We can do the same thing here. We can rewrite this logarithm into the exponential form of x plus 9 times x plus 15 equals 7 to the first power. 7 to the first power. And then, we have to do a little foiling here. So if we FOIL here, we get what? An x squared plus a 15x plus a 9x plus, let's see, 15 times 9 is 135 equals 7. Combine our like terms and subtract 7 from both sides. Gives us an x squared plus a 24x plus a 128 equals 0. And I hope that factors. It does. I'm not going to list all the factors of 128, but this factors to x plus 8 times x plus 16. Set each factor equal to 0 and solve. We get x is negative 8 and x is negative 16. Remember, check them. You don't want to have a bogus, an extraneous solution listed. So let's see, if negative 8 comes in here for x, okay, well that would be positive, which seems cool. And that would be positive. So I have a pretty good feeling about negative 8 being a solution. Check out negative 16. Put negative 16 in here for x. Negative 16 plus 9, negative 7. Can you take the logarithm of a negative number? No. So this is a bogus solution. It's an extraneous solution. And that's the final one of looking at this section where you're going to solve a lot of exponential and logarithmic equations. Hey folks, the last thing you'll see this week will be a brief look at some applications of exponential functions. And we're going back to an old topic. We're going back to compound interest. So I thought we'd look at this situation here. The question, how long will it take $5,000 to double if it earns 5.5% interest compounded? Part A, we'll look at it compounded quarterly. Part B, we'll look at it compounded continuously. All right, the key to this is you have to remember your compound interest formula. So let me write it down. A equals P times 1 plus R over N to the N times T power. So the 5,000, that's the principal. So 5,000 comes in for P. You also know what A is. How long will it take $5,000 to double? Well, that means how long till it becomes $10,000. So the A is 10,000. And you know 1 is 1. The interest rate, remember, put it in as a decimal. So it's 0.055. Compounded quarterly, so N is 4. N is 4. And we don't know what T is. That's what we're trying to solve for. But folks, this is just it's just an exponential equation to solve. No different than the ones we just looked at. I would start off by dividing both sides of this equation by 5,000. So I get 2 equals 1.01375 to the 4t power. Okay, if you're wondering, well, where in the world did this 1.01375 come from? I just simplified this. I did 1 plus 0.055 divided by 4. So I did that, added the 1, and that's what I get. So now how in the world am I going to solve this equation for t? Just like how we did in the prior example. Take the log of both sides of the equation. Use the preservation of equality for logarithms. Either take the common log of both sides or the natural log of both sides. I'm biased to the natural log, so I'll take the natural log of both sides. And notice, once you take the natural log of both sides, on the right side you're going to use law 3 of logarithms. You're going to put the 4t out front. So you have the natural log of 2 equals 4t, the natural log of 1.01375. And then, well, you can divide both sides of this equation by 4 natural log of that mess to get t equals the the natural log of 2 divided by 4 natural log 1.01375. That would be the exact answer. Remember, we just talked about exact versus approximately. Cranking it through the calculator, doing the natural log 2 divided by this mess, I get a decimal approximation of 12.689. And that would be 12.689 years. So a little over 12 and a half years. It'll take my $5,000 to double to $10,000 if it's at 5.5% interest compounded quarterly. Let's look at the continuous case. Remember, your compound interest formula for continuous compounding is A equals PE to the RT. You know P is 5,000. You know A is 10,000. That hasn't changed. The rate hasn't changed. It's still 5.5%. In fact, my first step of solving will be the same. Divide both sides by 5,000. So I get 2 equals e to the 0.055t. Now here, remember, I can take an exponential equation and rewrite it as a logarithmic equation pretty quickly. So this exponential equation, rewritten as a logarithmic equation, is the natural log of 2 equals 0.055t. Divide both sides by 0.055, and I get t is the natural log of 2 divided by 0.055. And again, this is the exact solution. The approximation, fire up the calculator, do natural log of 2 divided by 0.055, and you get t is about 12.603. And again, that's years. And that seems reasonable to me. It's a little less time continuously than quarterly. I mean, quarterly is 12.689 years and continuously is 12.603 years. That's a little less time. But that's a look at one example of an application that you'll see some in your e-text. And that concludes this week's preview video. Again, as I always mention, hopefully you get some benefit out of looking at these preview videos, but it does not replace reading your e-text and looking at the videos that are in your e-text. It's just meant to be a supplement. It's an overview, preview, however you want to look at it. But that's it. Thanks for watching.